This is Professor Hill, and this is Primary Production Part 2. Okay, so now you have an idea of what primary production is and a few of the primary producers on this planet. Basically, we're talking about the food chain, and the primary producers are the ones that take raw sunlight, raw water, raw gases, and make food out of them. Fix the carbohydrates into a form that the rest of us can use. So basically, you're talking about the plants of the world. And in this case, we're talking about the plants of the ocean, which, if you remember from the last PowerPoint, there's a lot of plants in the ocean. You know, we can have up to 100,000 of those little I'm sorry, not 100,000, 100 million little single-celled creatures in a liter of water. And remember, plants all breathe out oxygen. So a great deal of our oxygen comes from the ocean. So even if you are not a person that eats a lot of seafood and you don't care about the food web as far as that's concerned, you do care about breathing. I'm positive of it. All right, so what are the limitations on primary productivity in the ocean? One is sunlight, and two is the rate limiting nutrients. We've already talked a little bit about sunlight. I'm going to go a little bit more into it. Now, as it says there, the sunlight at the surface is often overwhelming for the photosynthesizers, meaning they don't live on the surface, most of them. If you've ever been near a body of water, it's the light that comes off of it is very, very bright. And you can actually get more of a burn, you know, a sunburn, if you spend time in the water, because you're getting the light from above and the light from below that's reflected off the water. Anyway, so a lot of photosynthesizers don't live just at the surface. Photosynthesizers have chlorophyll. They're plants, right? They reflect green light, which is why plants look green to us, because it's bouncing the green wavelengths off of the plant. But they absorb the red and the violet, which is why if people are trying to grow plants, a lot of times they'll put them under black lights. The black lights gives that violet light. So let's look here. We've seen this chart before where here's our different wavelengths, and this is how far in meters they penetrate below the surface of the water. Now they like the red, which is doesn't go very far at all. Okay, it stays right up at the surface, close to the surface. You know, it looks like maybe 3 meters at the most it goes down. The violet goes down a little further. You know, it can go up to 100 meters. That's like 330 feet. Okay, yes, red rarely penetrates below 10 meters, so most photosynthesizers live within those 10 meters, which is about 33 feet of the surface. Except for the photosynthetic blue-green algae. We've talked a little bit about them, I believe, in the last slide. They're one of the oldest life forms on this planet. They can synthesize blue and green light, and so they can go down a lot further. Okay. All right, so of course most photosynthesis occurs in the euphotic zone, the very first top of the water column. All right, so that's what I wanted to go into with light. Now let's do rate limiting nutrients. We've talked about them a little bit, okay, already, what they are. But once you have those rate limiting nutrients that have been fixed by either bacteria or photosynthesizers, and they're in the food chain, they've been eaten by animals, usually animals, and they're part of our body, and when we die, we decompose, and other organisms can still use those rate limiting nutrients that were fixed in our bodies if they can live off of decomposing flesh. Now, fecal matter also has those rate limiting nutrients in it, okay? When you defecate, or when any sea creature defecates, it's going to have some of those rate limiting nutrients in their feces. So when you're looking at something, this is called marine snow. Biological debris that falls from higher in the water column. So basically, decomposing things or fecal matter, but it's now no longer part of a living thing, and so it floats down. and it can end up on the sea floor, which is kind of a waste if you think about it, because you know, the photosynthesizers and the other creatures and the other processes that fixed these rate-limiting nutrients, now they've been fixed in a form that life forms can use, and now they're floating down to the bottom of the ocean. That's not good, right? Now, how do we don't want to waste them completely. You know, they'll pile up as sediments and eventually they'll become sedimentary rock. But do you remember when we talked about winds and how they can cause upwellings? Upwellings can return that marine snow, that biological debris, to the surface. And there it can be used again by some of the primary producers. And you can get a bloom. It's called a bloom when you get a whole lot of primary producers that are suddenly reproducing and doing primary productivity all at once. It's called a bloom. By the way, you remember, let's see here. They've got the north going to the left here. So if we look at the wind, which hemisphere are we in? The wind is going south up against a continent. I think it's rotating to the right. So if you're thinking north and northern hemisphere rotating to the right, we must be on the east side of the basin. And from the Coriolis effect and the Ekman spiral, it would cause an upwelling from underneath. If not, if you can't remember that, go back to the PowerPoints where we talked about that. Okay. Now, do you remember the thermocline, where there's a great sharp rise or falling of temperature in the water column? When there is little or no thermocline, the water doesn't change. It's better for upwellings. Upwellings can come from the bottom and up to the surface. These tend to only happen in the polar regions. Why? Why is that? That's because of convection. You remember convection? Warm things rise and cold things sink. All right. Let's just look again. Let's look at, this is about air, because I couldn't find one about water, but air, water, they're both fluids. They both, you know, they both act as fluids. So if you have warm air, and think this is the bottom of the ocean, if you have warm water or an upwelling, in this case an upwelling, the warm can go through colder stuff and go straight up. But cold cannot rise through warm. It doesn't work that way because cold is heavier than warm, so it can't push its way through. Warm is lighter than cold, so it can go through cold, but cold can't go through warm. All right, that's just convection. So, and again, think of this as water instead of air. Yeah, water. And you've probably seen thermoclines before. You know, you look out over the fields and you notice that the smoke's only going so high and then it's stopping. It's the same thing. The warm smoke is trying to go up and it's hitting a cold layer. Yes. The warm is going, wait, let me think. No, it's hitting a warm layer, sorry. And it can't keep rising. It's hitting a layer it can't go through. All right. So what we need is there to be no change of temperature as the upwelling happens in order to bring those nutrients from the bottom of the ocean to the top. So how can we do that? So let's look at our temperature profiles again. So here we got the low latitudes. Low means near the equator, near zero. The mid latitudes, that'd be like 30 degrees to 60 degrees. And the high latitudes, did I circle these? Bet I did. Okay, here's depth, you know, sea surface is 0 and down to 1,500 meters. And then we got low latitudes, mid latitudes, and high latitudes would be the polar regions, above 60 degrees or below 60 degrees. Now, if you look at the temperature profiles, you see that once you get up to about 450 meters, it's cold down below. You know, it's about freezing, about 4 degrees Celsius. We know that already. Most of the ocean is near freezing. And then in the low latitudes, near the equators, it starts to warm very quickly. And in the mid latitudes, it also warms very quickly. In the winter, it doesn't warm as much. Okay, that's what this dotted line is for. It's saying in the wintertime, it cools down up there. But in the high latitudes, it's cold year-round. So the temperature doesn't change. And so the upwelling that might come from the bottom of the ocean is not impeded by a temperature change that it can't rise through. And that's why a lot of primary productivity in the ocean happens near the poles. They're very famous for having lots and lots of sea life in them. That's what I just said. You can write it down. So here's primary productivity for a year in 97 and 98. The red shows you the highest primary productivity. Notice it's a lot of it's up here, you know, in the northern, this is Alaska, right? So all this is very high north, high latitudes. We got a lot down here near Antarctica. This here is where the Amazon River comes out, and so it's bringing a lot of sediments, which is giving rate-limiting nutrients that are washing from the rocks inland to the ocean. So that's the reason there's a lot right there. I'm not sure about here, although we're getting pretty high latitudes at this point. These lakes we're not going to even talk about right now. That's a different story. What I do think is interesting is that it's very high on the Greenland ice sheet. I was so curious about that I actually looked it up and found out that the Greenland ice sheet has lots and lots of very tiny microbial life that is actually it's a primary producer, lives on the ice. Anyway, you see that the lowest places of primary productivity are near the equator and in the middle of the ocean, the open ocean. These areas are virtually, as far as the ocean goes, they're deserts. They don't have as much life as further up and further down. So let's look at this by season and latitude. Latitude 0 to 90 up, 0 to 90 down. So where is it most productive and why? All right, these look kind of confusing, right? Looks like a game of Chinese jump rope. I don't know if they still do Chinese jump rope like they did when I was a kid. So we got a tropical ocean here. We have a North Pacific, so I'm assuming that's mid-latitudes. And then we got, yes, polar, all right, so high latitudes. Down here we see that the green lines are nutrients. The blue lines are nutrients, sorry. The green lines are the phytoplankton. Those are the primary producers. Green is good color for them, right? And water temperature is red. So let's start in the tropics. High water temperature, very low nutrients, very little primary productivity. Now we got the mid-latitudes. Okay, they have seasonal changes, very severe seasonal changes, right? Winter's cold. So in the cold, the water's cold, and then it gets hotter, and then it gets colder again, right? Winter, spring, summer, fall. How does that affect the nutrients? The nutrients are high, it looks like, when the water's colder. And when the water warms up, they get lower, and then they go up again. And then the primary productivity. It's clearly lowest in the wintertime, and then maybe this is when it is consuming the nutrients. It spikes in the spring and summer and falls off in the winter. Okay, so because you do need light. You need light for primary productivity, right? Keep in mind all the time, primary productivity comes from plants. So now we're in the polar regions. Low water temperature across the board. High nutrients across the board because they can benefit from the upwellings. But because there's no sunlight in the wintertime, above 60 degrees, wintertime is 6 months of darkness plus, usually there's ice covering the water, so if there was sun, they couldn't get through. They have to wait till the ice melts and the sun comes out, and then lots and lots of primary productivity, and then it goes back. Some of the big marine animals like the whales, they migrate, and they go up to the poles during the summer to eat, and then they come down to the tropics sometimes to breed and have their little babies, and then they go back up again. And that's why. So where's our primary productivity the greatest? Well, on this map, it looks like the mid-latitudes. But, well, let's go with mid-latitudes. That's what we're going to go by what the graphs say. And when is it greatest in the poles? Well, during the summer. So I also want you to notice that it is greatest when it's near shore, for the same reason that it's high over here near the Amazon, because near shore nutrients can be washed off from the rocks into the water, and so they can get some of those rate limiting nutrients that they don't have in the ocean. That's why they're rate limiting. This is a really, really interesting video. If you have a chance and a desire to see it, I would show it to you, but I'm having trouble with my CD right now. It's an Earth from Space video that I'll put the link in. I might even put it in the assignments and make an assignment out of it. I'll have to think about it. That's a good idea. I'll write a note to myself. Okay. That's a good idea. All right, carbonate compensation depth. What does that mean? Well, we've been talking about, fixing carbon, right? How primary producers take the carbon dioxide gas from the atmosphere, and they take the carbon out of it and fix it into plant. They make carbohydrates. What we got here is a graph, and what we're looking at there is the carbonate compensation depth. And what it means, the carbonate compensation depth, is the carbohydrates being produced by primary producers is equal to that being consumed by creatures that are higher up in the trophic web. So what would that be? Let me see if I got anything circled here. Okay, so we got depth. Here's surface. Here's 300. Aren't they going to even tell us if it's meters? Okay, meters. Oh, feet and meters. Feet below sea level. And here's photosynthesis. Now, this whole thing is photosynthesis. Everything under this curve. They're saying that if this brown area is the same, is being eaten, and the green, this whole thing is being produced. But there, as long as you're going to have plants producing things, you're going to have things eating plants. So, this brown part is the part that's being consumed right away. And they're saying that this green part here is the net productivity. Net, meaning the sort of the profit. There's that many extra plants that aren't being eaten, that are still staying there. So there's more being produced near the surface than there are being consumed. Now you notice that as we go lower and there's less and less light, you're going to have more of the animals and less of the plants. So you're going to have more eating and less producing. And here at this depth, about, well, let's see, 220 feet maybe, or 215 feet, or something like that, below sea level, the eating and the producing become equal. And now below that, there's no more, you're getting less and less and less photosynthesis, right? Until there's none at all. And so this is called the respiration rate. The respiration rate is what we do. We eat things and then we respire. We make energy out of it and we breathe out carbon dioxide. So basically, as it says down here, this is an oxygen minimum zone because there's more animals down here breathing out and no more plants really, except just a few, right, that are breathing oxygen out. That's kind of what that whole thing tells you. So anyway, to repeat, carbonate compensation depth is where the carbohydrates produced and the carbohydrates consumed are equal. And they call it carbon. Did they call it the carbon compensation depth? No, they're just calling it the compensation depth. I think it's usually called the carbonate compensation depth. I don't know. Maybe not. Notice it's at the bottom of the euphotic zone. The euphotic zone, right, is where you have your enough light to have primary production. Okay, there we go.